Hi everybody. Just going over a couple of review problems because I promised to. Although none of these problems here are going to be any different than the ones that you saw in the previous videos. But give you an opportunity to at least try the problem in advance, see if you could do it, and then come back and take a look at how I did it. So we'll start with this first one. Racing fuel, we're going to burn it, and as all combustion reactions, you get carbon dioxide and water vapor. So that gives us a good chance to use a little gas laws here. So 50 kilogram fuel tank is burned with isooctane. So 50 kilogram, usually we use grams, so that's really the only trick there. We do have a shortcut in the fact that we could use STP, that whenever we see STP conditions, we know that, first of all, mole ratios and volume ratios among gases are equivalent. And we also know that 1 mole of any gas is equal to 22.4 liters. So I'm going to use that. Let's copy this. And okay. So let's start with what they give us. Oh, I'm sorry. Yeah, pause the video, try the problem. I'll wait. Hey, you're back. Let's start with what they give me, which is 50 kilograms of the isooctane. And I'm going to multiply that and convert it to get grams. Since I need moles, and the periodic table is set up for grams per mole. If I look up the mass of isooctane, I do 8 times carbon plus 18 times hydrogen, and I get 114.232 grams, and that's for every 1 mole. And now I can use the balanced equation. Two moles of isooctane gives me, what do they want? They want to know volume of carbon dioxide. Oh, so we're doing our carbon footprint thing. So let's do, for every 2 moles of isooctane, we produce 16 moles of carbon dioxide. And since this is STP, I can do 1 mole of any gas occupies 22.4 liters of space. All right, so 50 times 1,000 divided by the mass times 16 divided by 2 times 22.4. And I get 78,436. So the volume of carbon dioxide is going to be 3 sig figs. So 78,400 liters. Okay, second problem. There we go, limiting reagent problem, and we use this Haber process for creating ammonia. And they give us 32 grams of hydrogen and 198 grams of nitrogen. And again, STP conditions, so I can do that shortcut. Not only can I do that 1 mole is 22.4 liters, but I can also do mole ratio and volume ratios are equivalent. So again, pause and give this one a shot, and I'll wait patiently. Hey, you're back. Okay. So limiting reagent, how do I know? Because I was dumb enough to put it right in the problem. But if I didn't have the word limiting reagent in the problem, I would know this is a limiting reagent because they're giving me 2 different amounts of reactant. So I'm going to stoich both of them to see which one is limiting. The one that gives me the least amount of moles of product is the limiting reagent. So let's convert this and look up hydrogen on the periodic table. And according to the balanced equation, for every 3 moles of hydrogen, we produce 2 moles of ammonia. So I get 32 divided by 2.016 times 2 divided by 3 10.6 moles. All right, so now we'll do the same thing for ammonia. Again, just look up the mass of nitrogen on the periodic table. So I would do the same thing for ammonia. I meant the same thing for nitrogen, the other reagent. All right, according to the balanced equation, 1 mole of nitrogen produces 2 moles of ammonia. So we can do 198 divided by 28.014 times 2. And I get 14.1 moles of ammonia. So my limiting reagent is going to be the one that produces the least amount of product. So this is my actual yield. And this is the chemical that is limiting that yield. We run out of hydrogen. So now that I know the yield, they want volume. So 10.6 moles of ammonia. And I know that for every 1 mole of ammonia, it occupies 22.4 liters of space. So we get 237 liters. All right. Okay, third problem. Molar mass given mass of an unknown gas and pressure, volume, and temperature. Okay, so like I said, there are some formulas, and if you want to go formula based on this, you can, but I like to take more of a conceptual approach. So molar mass is always grams of a material divided by moles. And they give us the grams right in the problem, 14.6 grams of the gas. So now we just figure out moles. If this was STP, I could use the volume to get the moles, but it's not. So I have to use PV equals nRT. Solve for moles. That is the worst N that I have done in the last 30 seconds. All right, pressure 1.184 atmospheres. You like that? You know, I sounded like all enthusiastic about the pressure. 18.0 liters. I can use the R value for atmospheres. And the temperature is already given in Kelvin, 291. All right, so how many moles do we have here? 1.184 times 18 divided by 0.0821 divided by 291. I get 0.892. Substitute that in. And I get a molar mass of 14.6 divided by 0.892. Or 16.4 grams per mole. Fourth problem, probably a density problem. Let's see, yes. All right, so they give me a density for helium at a certain temperature and pressure, but they're not giving me STP conditions. So again, intrinsic property, I can choose whatever sample I want, sample size, and it will still give me the same answer because it's proportional. So I'm going to choose a 1 mole sample. Okay, so again, define what it is that we're trying to do. Density. Mass over volume, and they give us neither value because density is an intrinsic property, which means that it is not based upon the amount, it's only based upon the identity of material. So we can choose whatever sample size we want. So the sample size I'm going to choose is 1 mole of this gas. And if I look up 1 mole of helium on the periodic table, I get 4.003 grams for 1 mole. So that gives me a mass, 4.003 grams of helium. All right, so now I just need the volume. And so since this is not an STP problem, I got to use PV equals nRT. Solve for volume. I'm using a 1 mole sample, and they gave me atmospheres, so I can use 0.0821 liter atmospheres per mole Kelvin as my gas law constant. They were kind enough to give me Kelvin instead of Celsius. I won't be that nice on the test because, like I said, if we were doing labs, we're measuring it in Celsius. And we're going to divide that by 1.17 atmospheres, which case on test, I would most likely put millimeters of mercury because barometers and manometers use millimeters of mercury as their unit. All right, so let's see what we got. 0.0821 times 293 divided by 1.17 atmospheres. I got 20.6 liters. So I can take that and substitute it back into my density calculation. So the density of helium at this temperature is 0.194 grams per liter. Right? Easy. Put a whole bunch of those on the test as long as you remember that intrinsic means you can choose the sample size. And the last one, wanted to throw in one good stoichiometry problem. Oopsie poopsie. Alright, so this is one I stole from online sources. And let's see what they give us here. Alright, so they give us a reaction. 2 elements synthesis reaction for potassium chloride. And it's already balanced. And they say, what mass of potassium... All right, Alexa, I got my Amazon notification. I think my new Mac computer is here so that my slideshows and everything start looking a lot nicer. Anyway, what mass of potassium chloride forms when 5.25 liters of chlorine at a certain temperature and pressure reacts with 17 grams of potassium? Now, I know this is a limiting reagent problem. Again, they were kind enough to put the word limiting reagent up here. However, it won't be like that on the test. I know that it is a limiting reagent because they're giving me values for chlorine and they're giving me a mass for potassium. So they're giving me both reagents in the balanced equation. So that means I'm going to have to go back and do a limiting reagent problem with it. But I also threw in a percent yield. I said, all right, we're going to figure out the amount of theoretical yield, but if a student collects 26.8 grams of potassium chloride doing this lab, what is the actual percent yield? So I changed the problem just a little bit. You know what? Let's do this. No. Has it really been that long since I've used this thing? Here we go. Copy. And we can paste that down. All right, let's expand it a little bit. Okay, so limited reagents. So I'm going to start with, let's stoich both of these reagents. We don't know how many moles of chlorine we are dealing with, so let's start with that. They give us a pressure and a temperature, but it's not STP, so we're going to have to use PV equals nRT. Let's solve for moles. And now I can substitute in my pressure was given. My volume was given. I can use the gas law constant for atmospheres. Atmospheres per mole Kelvin. And then again, they were nice enough to give us a Kelvin temperature. All right, so how many moles of chlorine did we actually have? 0.95 times 5.25 divided by 0.0821 divided by 293. 0.207 moles of chlorine. Now, let's see if it's the limiting reagent. We're going to figure out how many moles of product we get from the balanced equation. As it turns out, it's a 2-to-2 mole ratio. So here's the documentation. Of course, if I was doing this on a multiple choice test, I wouldn't bother to document this out. I would just quickly go for the answer. So 0.207 moles of potassium chloride. Now let's do the same thing with the potassium. They said, I think it was 17 grams, but let's check, make sure. Yeah, 17 grams of potassium. Convert that to moles. And then I know, according to the balanced equation, I think it's, what do we got here? Oh my goodness gracious, first of all, I just made another mistake. It is not a 2-to-2 ratio for chlorine to potassium chloride. If I looked a little carefully, it's 1 mole of chlorine for every 2 moles of potassium chloride. I'm hoping with the Mac that I'm able to do some editing, because when I make mistakes like this, I'd rather go back and edit it. But I'm just basically using photos from my tablet. Not that you care. Anyway, so this is 2 moles of potassium for every 2 moles of potassium chloride. And that gives me 17 divided by 39.098. 0.435 moles of potassium chloride. So this is my limiting reagent because this is my yield. My yield is the lower amount between the two, 0.407 moles. So that makes chlorine the limiting reagent. And now that I know that this is my yield, I also have to know that this is theoretical yield. And we said that the student collected 26.8 grams, so we can do percent yield is equal to theoretical yield. Oh man, not a good day for me. I'm sorry. Actual yield divided by theoretical yield times 100%. And so now I can substitute in. Right? Well, let's see what our actual yield is. We said that our yield is 0.407 moles. And I'm going to convert that to grams. Look up the values on the periodic table, 39.098 plus 35.453 and so my theoretical yield was 30.3 grams. Alright, so I can substitute that in. Actual yield the student got was 26.8 grams. Theoretical with 30.3. So that is 88.4% yield. Okay, and I hope that helps you with that. You know, I like the percent yield problems, limiting reagent problems, so I tend to emphasize those that are a little more difficult. As far as the review of the actual test, you can just go to that document that I had posted for the Chapter 18 test. I mean, it had both 18 and 19. The things that weren't on Chapter 18 test will, of course, be on the Chapter 19 test. All right, thank you very much.